Okay, so now we'll move on with exercise 4C. So this exercise is also basically it's continuation of horizontal circular motion. Okay, so you have more complicated, I mean more a little bit more challenging sums when it comes to the horizontal circular motion. Okay, so let's see how to first we need to learn to construct the diagram. Okay, so basically the principles are remaining the same. You will always apply vertical equilibrium and if equal limit was the center, those concepts remain the same. But the diagrams are the key here. Okay, drawing the force diagram is what's really important. Okay, let's see. Okay, they say a particle of mass 1.5 kilogram is attached to one end of a light inextensible string of length 60 centimeters. Okay, yeah, I think we can picture that, right? You have a mass 1.5 kilogram. There's a string of length 60 centimeter. Particle is attached to the end of the string. Okay. The other end of the string is attached to a fixed point A. Okay, so there is a fixed point called A. Okay, I'll name the fixed point A here. The other end of the string is attached to the fixed point A. So the other one end is attached. The other end has the particle. Okay. The particle moves with constant angular speed in a horizontal circle of radius 36. Okay. Now you can see the length of your string is 60 centimeters, right? Now basically you have the string. Okay, so the string was 60 centimeters, right? So they are saying now if you consider this as particle A, they are saying this particle P, this particle moves with a constant angular speed in a horizontal circle of radius 36. Okay, so what's going on? And they say the center of the circle. Now this particle is moving in a circular motion in a horizontal circle of radius 36, and they say the center of the circle is vertically below A. Okay, so do you picture what's going on here? The center of the circle is vertically below A. Okay, so this is, let me draw the center of the circle. So center of the circle is vertically below A. Let's say this is the center. And so where's your particle then? So your particle is going to be, it's performing a horizontal circular motion. So can you guys, can you see what's going on here? So your particle is going to perform a horizontal circular motion. Can you see? So it's performing a horizontal circular motion with radius 36 centimeters. The length of your string is 60 centimeters. Okay, and then the particle is performing a horizontal circular motion. The center of the circular motion is directly below A. And you see, so this is the diagram. Basically, this is the basic diagram that you first need to consider. Okay, so guys, I hope you can do the transition here and understand what's going on, because I think some of you might be thinking that the fixed point A, since we were dealing a lot with horizontal circular motion in the previous section and we just moved to the new section. So most of the time you might be thinking your particle fixed point here and the particle is like this, right? Horizontally directly across and then moving in a circular motion like this. But if it goes like this, you know the length of the string is 60. And if your particle goes in a horizontal circle like this, the radius of the circular path is also 60. But they say here very clearly the particle moves in a circular motion with radius 36. So radius is not the full length of the string. So it's a different circle. Okay, and also they say the center of the circle is vertically below A. So whatever the circular motion you are doing, it's vertically below A. So that's why we need to draw a refined diagram like this. Okay, so diagrams are now going to be slightly different than what we did in the previous exercise. Okay. All right. So now it's time to mark the forces and time to mark the forces and go with our concepts. So what are the forces we have here? Number one, you have a string, therefore you have tension. Okay, so there's tension, and what else? We have the weight. We have the weight 1.5 g. Okay, so I think these are the only two forces you have here: the tension and the weight. However, you can see in this case the tension is going in a slanted direction, which means you will need to consider components of tension. You will have to consider components of tension. So to get the components of tension, you will need to calculate the angle here. Okay, shall we get the angle theta here? I want this theta angle. So how do we get the theta angle? So you can see we have a right angle triangle. This is definitely a right angle triangle. So theta adjacent over hypotenuse. Cos theta adjacent over hypotenuse. So how much is it when you simplify? 6 over 10. 3 over 5, right? Cos theta is 3 over 5. Can you see? So don't go to get the theta angle. Okay. Do not use cos inverse and get the theta angle, because that would give you a decimal. We are trying to keep this in exact form as much as possible. Okay, so in M3, even in M2, in M1, when we were working with these angles, we like when it comes to force diagrams and calculating angles, we always took the cost ratio, sine ratio, because we just need the cost ratio and the sine ratio. Okay, so I have the cost ratio 3 over 5. So from that, I can build up the sine ratio. I think some of you, when you see that the cost ratio is 3 over 5, you immediately know the sine ratio, isn't it? Because this is a triangle. I mean, you can draw another triangle here for the theta. The cost is adjacent over hypotenuse. So adjacent is this 3, hypotenuse is 5, and by using Pythagoras theorem, you know the other side length is how much? So this is the hypotenuse is 5. If this is 3, this side should definitely be 4, right? Because this is 5 square minus 3 square square root is 4, right? Pythagoras theorem. I'm just using Pythagoras theorem. So basically, sine theta is opposite over hypotenuse. It's going to be 4 over 5. Okay, so if you have practiced M1 and M2 enough, I think you might remember if cos theta is 3 over 5, you can immediately recall that sine should be 4 over 5. Okay, and that's like one of the simplest triangles you have. All right, so now time to apply the concepts. So what are the concepts? We need to consider vertical equilibrium and F equal ma towards the center of the circular motion. All right, so what's the vertical equilibrium here? I think you can see vertically we have downwards 1.5 G. So what's the other force that's acting upwards? Basically, it's the component of tension. So guys, can you see that the component of tension acting upwards is what? It's P sine theta. Can you see? So it's T sine, because away from the angle it's sine, and T cos theta is what's acting towards the center. T cos theta acts towards the center, T sine theta acts vertically. Right? T cos theta is horizontal, T sine theta is vertical. That's done. All you have to do is now what? Apply the rule. So we'll consider vertical equilibrium. So when you consider vertical equilibrium, you can write here T sine theta. T sine theta equals 1.5 G. So T into sine theta is 4 over 5 equals 1.5 G. T equals 1.5 G into 5 over 4. Shall we get the answer for T in terms of G? It's better to keep it in terms of G. And at the in that case, you can give your answer in exact form. So 1.5 into 5 over 4. How much is it? All right. So 1.5 into 5 over 4 without giving the G value. Okay. So we want to preserve the exact form as much as possible, because we are not yet at the end. Okay. So 1.5 into 5 over 4 is 15 over 8. Isn't it? 15 over 8, and the G is on top. Okay, so tension is 15 G over 8. Okay, actually they're asking you to calculate the tension in the string. So basically you could leave your answer like 15 G over 8 is also a final answer, or else you could give the G value as 9.8 and give your answer to 2SF or 3SF. Okay, and that's how much? So either you can leave your answer as 15 G over 8, or you can use G value as 9.8 in the cal and get the answer as how much do we get? Let's type it in the cal. Okay, so that's 18.375. Okay, so 18.375, but you should not keep it more than 3SF when you're using G as 9.8. So it's 18.375, so 18.4 newtons. Correct to 3 SF. Okay, so in the exam, they might say you to find exact values. Sometimes they might ask you, if you input the G value, you should give the answer to 3 SF. Okay, so both of them are okay. Both of these forms. Okay. And then calculate the tension in the string, that's done, and the angular speed of the particle. Okay, so you're supposed to find the omega. So in order to find omega, we will have to use F equal ma towards center. So let's use F equal ma towards the center, center of the circular motion. So basically, who is the center? This is the center of your circular motion. So when you use F equal ma, who is the force acting towards the center? The only force acting towards the center is T cos theta. T cos theta acts towards the center, right? That's the centripetal force. The weight and T sin theta, they're acting vertically. So only T cos theta acts towards the center. So that's the centripetal force equals mass. Mass is 1.5 kilograms, right? And centripetal acceleration, either you will use V square over R or R omega square. Since I'm trying to find omega, I will use R omega square. All right, so we have the t value, and when you're using the t value, do not use the 3SF, but use the exact answer. Okay, use the exact figure for t. So the exact figure is 15G over 8, or else in this case, you could use the full decimal. Okay, so 15G over 8, that's the t value. Cos theta was 3 over 5. Yeah, cos theta is 3 over 5 equal 1.5 into what's the radius of the circular motion? The circular motion has radius 36 centimeters, which should be converted to meters. So that's 0.36 meters into omega square. And now you make omega the subject. Okay, so you make omega the subject. So you get here 15G into 3. I think all the other guys are down, right? 8 was already down, 5 is already down, and we'll bring 1.5 into 0.36. Guys, can you see? 15G into 3 is in the numerator, 8 into 5 is denominator, and 1.5 into 0.36 also comes down to the denominator. And then you take the square root of the whole thing and you can get the value of omega.
TC, can I multiply and
So guys, over here you can see I've typed the whole thing in the cal. 15 into G is 9.8. So if we give the G value as 9.8, then you will keep the answer 3SF, okay, or 2SF. Into 3 divide by, so you can say 8 into 5 into 1.5 into 0.36. So you get the answer for that. Okay, so the answer is 245 over 12, and you have to root it because this is omega square. Okay, so omega square is 245 over 12. So root of the answer, and that's so don't leave the third form. Okay, that should be 4.51848, which means definitely you correct it to 3SF or 2SF. So I'll go with 3SF, 4.52. So omega is 4.52 radians per second. Okay, so this is your answer. Okay, so let's move on to question number 5. Okay, so they say a conical pendulum consists of a light inextensible string AB of length L fixed at A and carrying a small ball of mass M at B. The particle moves in a horizontal circle with center vertically below A. The center is vertically below A at constant angular speed omega. Find in terms of M, L, and omega the tension in the string. Okay, so basically, I think when you read this question, you can see the type of question is very much similar to what we did in question number 1, right? So you have a fixed point A. Okay, you have the fixed point A, and then you have the particle. Okay, so you have the pendulum, and you have a particle moving in circular motion. And so the center of the circle is vertically below A. And so the particle moves in a circular motion. Right, so this is what we have. The particle moves in a circular motion. And let's mark all the information. The length of the string is L. Okay, and they say the mass is mg, mass is m, which means weight is mg, right? And then the particle moves in a horizontal circle with center vertically below A at constant angular speed omega. Okay, fine. In terms of m, L, and omega, the tension in the string. Okay, so the tension in the string is T. You can see it's the exact same forces which we marked previously. Okay, so then you know what's to be done here. The same story, just that you have the tension components are what's going to come here for the vertical equilibrium and the weight. So you can mark here. So we'll mark theta here. So in which case this is T sine theta, right? T sine theta is balancing with the weight for vertical equilibrium. And you have here T cos theta, which is the force acting towards the center. Agree? So this is my force diagram. So they're asking you to find in terms of this M, L, and omega. In terms of M, L, and omega, you're supposed to find the tension in the string. Okay, so you're supposed to find the tension. Okay, so let's do the things that we know. First thing is, however, the theta. We need to get a equation for theta. So the length here is L. Shall we put the radius as R? But I mean, I'm inputting the radius as R, but R is a variable, a constant that I'm in. Okay, so R should not be in the final answer. Okay, so but for now, just to get started, if I input R here, okay, so this is going to be, let me draw this there. If this is theta and if this is L and this is R, I need a equation. So over here, okay, so let's just keep this in mind at the moment. Okay, so this is the length and this is the R. Okay, let's keep it like this for now and let's go for the equation. Okay, all right, so first one, vertical equilibrium. So when I consider vertical equilibrium, it's T sine theta who is equal to mg. Okay, so it's T sine theta who is equal to mg. All right, and let's apply F equal ma towards center. So towards the center, what are the forces we have? So towards center, we have T cos theta. Okay, T cos theta is the only force who is the centripetal force basically. Mass is m. And acceleration, since we want to find in with terms of omega, we will use uh, m r omega square. So we use r omega square. Okay. All right. So then over here, I want to find the value of tension. Okay. So let's make T the subject in one equation and substitute to the other. Okay. So I get here T equals mg over sine theta, right? Right. Okay. T is mg over sine theta. Agreed? All right. And then let's input the value here. We're supposed to find the tension, right? Yeah, we're supposed to find the tension. Okay. Okay, so if I substitute the t value here, I'm gonna lose it, right? Yeah. Okay. Okay, so how do we proceed now? Okay, so instead of going in that part, I think one of the easiest things you could do here is with this triangle, okay? I think you can see we can easily get the answer for the cost ratio, isn't it? So cost ratio, if you take it from this triangle, cos theta is adjacent over hypotenuse. So adjacent is R, hypotenuse is L, isn't it? Cos theta is R over L. Can you see? So that's an easy substitute that we can use over here. So T into cos theta is R over L. Okay, equals mr omega square. Now I told you R is a value that we input. So R shouldn't be a part of our final answer. So do you see what we get when I make T the subject here? L times mr omega square divided by R. And you can see R clearly cancels out. Okay, and can you see we get the answer in terms of m, l, and omega? So the tension is m, l, omega square. That's it. So this is all they want. Okay, this is all they want you to find. It's actually the vertical equilibrium was not even, we didn't even get a chance to use it. Okay, so in this case, because they want the answer in terms of ml and omega, so the theta that you found needs to be replaced. So it was easy to replace the theta directly using cos theta, r over L. Okay, so it's done. So this is the answer for the tension. Okay, so let's move to the next type of question. Okay, so the next type of question is, okay, so we are now going to work with a hemisphere. Okay, so let's see how it's done. Let's say a hemispherical ball of radius r centimeter is resting in a fixed position with its rim horizontal. Okay, so the rim is horizontal. A small marble of mass m is moving in a horizontal circle around the smooth inside surface of the ball. The plane of the circle is 3 centimeters below the plane of the rim of the ball. Find the angular speed of the marble. Okay, so basically it's once again the diagram. Okay, so let's construct the diagram. First thing is you must get a hemisphere. So a hemisphere, the rim is horizontal and the bottom of the hemisphere is touching the ground. So let's draw this. All right, so you can see there's a hemisphere here. Okay, so the hemispherical ball of radius r centimeters. Okay, so radius of the hemisphere is r centimeters. Okay, with the rim is horizontal. A small marble of mass m is moving in a horizontal circle around the smooth inside surface of the ball. So inside the surface, you have a marble that's moving in a horizontal circle, and they say the plane of this circle. So basically, when the circle moves, it moves on a circular plane, and the plane of the circle is 3 centimeters below the plane of the rim of the ball. So basically, the circle is 3 centimeters below the circular plane, the center of the circle. Okay, so which means your circle is moving in a circular path, which means your particle is moving in a circular path on the inside surface of the hemisphere. Okay, so they're asking you to find the omega here. They're asking you to find the angular speed of the ball. Okay, so how does it work? Okay, so this is basically how the diagram looks. Okay, so you have a hemispherical ball, the radius is r, and you have a marble which is moving in a circular motion around the inside plane of the hemisphere. Okay, around the inside plane of the hemisphere, you have this marble that's moving. All right, so you are supposed to find they're asking you to find the angular speed. Okay, so once again, in horizontal circular motion, you just have to do the two things. What is it? You apply, you consider vertical equilibrium and you apply F equal ma towards center. That's it. But in order to do that properly, you need the proper force diagram. Okay, so now the next thing is to mark all the forces acting on the particle. So let's mark all the forces. All right, so the first thing we have here is the weight. So the mass, marble of mass m, which means weight is mg. Weight is mg. And what about the norm? And the other force you have here is the contact force, because you can see the marble is in contact with the hemisphere. Therefore, you have normal reaction, and you know normal reaction is now is perpendicular to the surface. So you have a, I mean, this is a hemisphere. So basically, it's a circular surface. So if you have any circular surface, okay, and say you have you're drawing a perpendicular, normal reaction is perpendicular to the circular surface. Basically, it's perpendicular to the tangent at this point, right? So if it's perpendicular to the tangent at this point, what do you recall? So this particular line, if you are perpendicular to this surface, then it must definitely pass through what? It must definitely pass through the center of the circle. Isn't it? When you have a circular path, when you have a circular kind of path here, and if you have something, if you line you draw, makes a perpendicular to the circular surface, which means that particular line, it's like the radius of the circle. Radius and tangent are perpendicular, right? So this must definitely what? Go through the center. So that's exactly what we have over here. Our normal reaction is perpendicular to the surface. So it's a circular surface. It must definitely pass through the center of the hemisphere. So that's really important. So this is the normal reaction, and it's really important that you understand it goes through the center. The line of action of the normal reaction passes through the center of the hemisphere. That's really important. Okay, because it makes a perpendicular to the surface. All right, and then let's consider the center. Okay, so now you're supposed to find the angular speed of the marble, right? Okay. So how do you find the angular speed? Again, the theory is exactly the same. So what you do is you apply F equal ma towards the center, and you consider the vertical equilibrium. So again, we'll use the theta value here. So I will consider this as theta, and you'll have to go for the components. So components, you have R sine theta acting upwards, and you have R cos theta, who is going to be the centripetal force acting towards the center. All right. Okay, so let's consider the right angle triangle and try to get some substitutions for theta. Okay, so let's try to get some substitutions for the theta. So this is the right angle triangle that we have in the middle. So can you see the right angle triangle? Okay, basically I'm drawing this triangle. Okay, so this is the triangle that I've drawn over here. Can you see? Okay, it's the same triangle I've drawn over there. Okay, so this is 3 centimeters. This is 3 centimeters. And guys, what about this? What about this length? I think you can see over here, this particular length is what? If you consider this particular length, this is the radius of the sphere, isn't it? Can you see it's the radius of the sphere? So radius of the sphere means it is, I mean, they have told the radius of the hemisphere. The radius of the hemisphere is simple r, which means because if this is also, you can clearly see it's from the center of the hemisphere to the surface, which means this particular length is simple r. So that's really important. Guys, can you see? And then the other side length. So over here, this length is the, basically it's the radius of our circular motion. So this will be, when you use Pythagoras theorem, it's gonna be r square minus 3 square, isn't it? Square root. Guys, do you see what I did over here? I use Pythagoras theorem. Can you all understand? When you use Pythagoras theorem, from the hypotenuse square, you subtract the square of the other side, right? R square minus 3 square, and then you square root. Basically, it's r square minus 9 root, this length. So this length over here, or in other words, the radius of our circular motion, okay, our horizontal circular motion is root r square minus 9. Okay, guys, do you, I hope you guys can, understand. Okay, guys, so radius of this is root r square minus 9, the length, okay? Okay, so just a heads up. Okay. Right, let's now move on to the sum. So let's go consider vertical equilibrium. All right, so when we consider vertical equilibrium, what do we get? So r sine theta. R sine theta is equal to mg, isn't it? Yeah, I think this was our theta, right? Yeah. So r sine theta is equal to mg. So I think we can input the sine theta value. Sine theta is opposite over hypotenuse, right? Sine theta opposite is 3. Hypotenuse is r. So we could input that. 3 over R. So normal reaction equals mgr over 3. Right, so I get here normal reaction is mgr over 3. Okay, then let's apply F equal ma towards the center of the circular motion. So towards the center of the circular motion, the centripetal force we have is r cos theta. Guys, can you see? It's r cos theta. So r cos theta equals mass is m into acceleration. So for acceleration, you can use either r omega square or v square over r. So since I want angular speed, I'll go with r omega square. Okay, so r omega square, guys, over here you have to be very cautious with this r. Okay, this r doesn't mean the radius of the hemisphere. The r here represents the radius. I just put here r1 or something just to say that it's the radius of a circular bar, because you need to understand r is the radius of a hemisphere. But when you use mr omega square, the r is supposed to represent the radius of the circular path. Okay, so the radius of the circular path we already found. So what's the radius of the circular path? Radius of the circular path is root r square minus 9, this length. Can you see? So this length is root r square minus 9. That's the radius of the circular path. Into omega square. We're supposed to find omega, right? Okay, we're supposed to find omega. I think we can get the cos theta also, and r value also I know. R is mgr over 3 into cos theta. Guys, what's cos theta? So over here, if you get the cos theta ratio, cos is adjacent over hypotenuse. So adjacent is r square minus 9. Adjacent over hypotenuse is r. Guys, can you see? So cos theta is adjacent over hypotenuse. So r square minus 9 over r. Agreed, equals m times root r square minus 9 into omega square. So I think you can clearly see root r square minus 9 will cancel out in both sections, right? Because it can come down as a division, it cancels out immediately. So even simple m cancels out. And then you can see what's remaining. So you're remaining with, even the r cancels out, right? Even the r cancels out here. So I get g over 3. That's all right. G over 3 equals to omega square, which means omega is root g over 3. So omega is root g over 3 radians per second. So this is the answer. Okay, so I hope all of you understood this properly.